computer, then to record from that since I'm going to be projecting. Okay. So is this, how long is this one? Looks pretty good. Yes?
Is your last name spelled wrong?
Not just my last name.
Ah.
So this is a variant of a talk I gave. Anybody know where this talk was given? Cincinnati, be more specific. At what event? At Math Fest. And so as a nice twist, when I sent in my abstract and title, they sent it back to me a week or so later corrected. And then they sent another email, oh wait, was that on purpose? So the corrected title, which I think you were all able to get. So is it really that hard to go back and forth between the two? And given that I want to talk about the Cincinnati Bungles later today, I think it's actually fitting that this talk was given in Cincinnati. They had as many wins on August 1st as they do today. So why was it so easy for you to decipher this?
Because we already know words.
You already know a lot of the words. In fact, I deliberately did not adjust my email address or the web link. But a lot of the other stuff you can read without too much trouble. So what I want to do today is I want to talk about the science of error detection, error correction. This leads into some extremely interesting mathematics, in particular sphere packing. So one of the possible classes that I might teach next year is a class on sphere packing. One of the great successes of linear programming was to solve a conjecture that was just a little bit older than Fermat's last theorem and fell just a little bit after Fermat's last theorem. So it was open longer. If you have a bunch of cannonballs, perfect spheres, what is the best way to pack them so that you have the greatest density of space covered? And the answer is the blatantly obvious. You put them in a nice hexagonal pattern in the plane, and then you have valleys, and then you have another hexagonal pattern, and you put it so that the balls go into the valleys, and you just lather, rinse, repeat. But proving that this is the case, that this is the best, was actually quite challenging. In 2 dimensions, it's much easier. In 1 dimension, it's trivial. It turns out in higher dimensions, a lot is known and a lot is not known. Certain dimensions turn out to be easier to work with than others. And there's a lot of really good number theory that comes into play. So the key breakthroughs were made by Thomas Hales back when I believe he was at Michigan with one of his graduate students. And he was finally able to, in a series of papers, solve the sphere packing problem by reducing it to a very large but also very finite computation. So I think it was a 150-dimensional linear programming problem. In terms of what you would do is you would look at all these different ways to pack spheres. And for each one of them, you would vary things a little bit and try to see what density of 3 space does it cover. And you would have upper and lower bounds for how much of the 3 space you would get. And you would just have to have those bounds close enough so that at the end of the day, you could say that your answer was a lower percentage than the standard grossest packing of spheres or oranges or fruits like that. And the difficulty was that for some of the configurations, the upper bound was just a little bit above what you would get with the best packing. So it took a while to come up with a linear programming problem that could work. So there is a brief summary of this in the book. It's one of the latter chapters. The chapter before that is on another great computer-aided proof, the 4-coloring conjecture. If you have a nice set of regions, 4 colors suffice. Can anybody give a state that would not be considered nice? If it helps, I was a postdoc at Ohio State. Michigan. So why does Michigan suck? And I know that this could take a long time. So let's focus on a mathematical reason why we may not like Michigan. Yes? Yeah, there's a disconnected part in Michigan. And so if you have disconnected states, then you can easily imagine a configuration where you would need more than just 4 colors, because you can keep playing terrible games like this. Fortunately, we can still color things even with Michigan. But the first proof of the 4-coloring theorem was in the 1800s, and it was wrong. And there were things and cases that were missed. So there's a nice chapter on this in the book as well. When the first correct proof came out, there was a good amount of computer code that was used in this. Same thing with Hales's proof of the Kepler conjecture. And the mathematics community has trouble dealing with proofs like this. Some subjects don't worry about this as much. The trouble is, can you trust the code? Can you make sure that every case has been covered? Well, we have those concerns as well about just general math proofs, which have hundreds of pages of very long technical arguments. And in fact, the reception that the proof got influenced Hales to change his math research. And he now works in almost, I guess the best way to phrase this, like automated proof theory, where you actually design computer programs to actually do proofs and give you proof certificates. So I want to talk a little bit about error detecting, error correcting code. So this is not a class in cryptography. I'll just go very briefly through some of the basics. If anybody ever wants to know more about this stuff, always happy to chat. It's enough to just send zeros and ones. We do not need to send A, B, and C. So if I want to use 5-digit blocks, that gives me 32 possible characters. So I have 2 choices for each. So I can get every letter of the alphabet plus a couple of punctuation marks. And I probably want to have 0 and 1 encoded somehow, because if I can then write numbers in binary, I can write everything. If you want more, what you could do is you could do 6-digit blocks. There's a lot of things you could do. So when we do information transfer, we want to transmit information, and we want, hopefully, just the intended recipient to be able to determine what was sent. So this is where we have a tremendous generational gap, right? Is there anybody here who remembers a time before Google? Okay, so there's 2 of us who remember time before Google. I remember where I was the day I heard about this website called Google that you should check out. It was not a default. Does anybody here remember dial-up modems? Okay, so we've got 3 people. It's getting a little bit better. Anybody remember floppy disks and using floppy disks? Oh, okay, even better, okay. Anybody remember using tape cassettes for your computer programs? Oh, my hands all go down. So I had a Timex Sinclair 1000 where it would take us 7 minutes to load up Flight Simulator, and it would be essentially lines and circles. But they would at least be colored, so it's not horrible. If you want a terrific video to watch is the evolution of Madden football, and use like 25, 30 years of how the game has changed, just what the special effects and graphics are now versus how they started. A lot of the issues do not matter nearly as much today as they did 20 or 30 years ago. I'm not even going to bother asking how many people here have a cell phone. Your cell phone, I believe, but it's nice that I don't even have to ask and you will answer, so thank you. I believe your cell phone has more power, more computational power than the Voyager space probe. And so every couple hundred years, the outer planets align perfectly, so you can launch one probe and visit all of them. Unfortunately, that time was not when NASA was ready to launch a probe. So what they did is they launched the best probe they could at the time, and then they upgraded the probe as it was traveling. Now, you can't really physically change things, but you can change the code. And so when they are having Voyager transmitting images from millions and billions of miles away, any efficiency you have is going to be incredibly important, especially when you consider the difficulty of sending the message and the likelihood that some of the message will be garbled and trying to figure out what was intended. So nowadays, we can afford to be a little bit less concerned about how much things cost and how much space things take up. But these are still issues. I'm trying to think. The first memory expansion I remember getting from one of my computers was a 16 kilobyte RAM pack. I don't even know if 16 kilobytes is at the size that anybody would even notice anymore in terms of just how much things have changed. So when I was giving this at MathFest, somebody had used this TV show in their talk beforehand, so I quickly modified. So the cultural extra credit, what TV show? Yes, Futurama. What number is represented?
This is bad.
Yes, it's backwards. Yes, it's 666. It's the number of the beast in binary backwards. And so it's not until later in the episode when the robot sees it reflected in the mirror that he starts running away screaming. Yeah. You've got a lot of math geeks who write for The Simpsons and Futurama, and they occasionally put in stuff like this. All right. So just quickly, the way RSA works, in case you've never seen it, is you typically choose 2 primes and you keep them secret, P and Q, and then N is going to be their product. And you choose 2 numbers, E and D, such that E times D is 1 mod P minus 1, Q minus 1. So what it means is when you divide it by P minus 1, Q minus 1, it has a remainder of 1. I'm not going to explain why all this works, but if you take some message M, then you send M to the E mod N. So you raise it to the E's power, and then you take the remainder when you divide by N. We've seen early in the semester how to do fast multiplication, repeated squares. So it's actually not hard to raise a number to a 400-digit number. We can do that very rapidly by writing the 400-digit number in binary. So this can be done quite well, quite easily. I'm just choosing small numbers so as not to overload the screen. And we get the following number. And then the way you decrypt is you raise it to the Dth power. And so if you've taken abstract algebra, what's really going on here is we have a group, and we have an order of the group, and that's why all of this works. A lot of the other encryption systems is you do like a letter swap. A goes to Q, B goes to R. And if you have something like that, if you have 1 or 2 transmission errors, you can still detect most of the message, and you can get the rest from context. So over here, imagine we receive something which has 1 digit off. We were supposed to have a 7, we got an 8. When we try to decrypt it, the message is extremely different. You were supposed to get 12120947, you get 1211411028. So if our numbers are supposed to be blocks of letters, it's very different. Are you surprised that some of the digits were the same? That we did get some of it right? Why not?
Random numbers.
Yeah, random numbers. So what percent of the time do you expect randomly that we should be right? About? 1 in 10. And so, given that our number is only around 10 digits, you would expect maybe 1 plus or minus 1 digit to be correct. So this is not unreasonable. All right, so I'm going to concentrate on error detection and error correction. So the first part, the easy part, is detecting that you've made a mistake. The harder part is figuring out how to correct it. So one of the greatest advances in the 20th century was the barcode scanner system. So I think we've talked a little bit about why this is so good. What's the benefit of the barcode scanner? Yes. So speed, what else? So related to the speed is that the worker doesn't need to know what the prices are for everything. But there's another huge advantage of the barcode scanner. Yes? It makes it much easier to maintain inventory. You no longer have to pay people to be going around. You also have the ability to do correlated purchase analysis, and we discussed target with that in a previous class. But the ability to do live inventory. How many of you have ever been at a supermarket or a store where you've had them scan an item and it doesn't work? And then you just give up and you don't buy the item, correct? What happens? Is that what they do immediately? They put in the number?
Usually that's what happens. So like do it manually.
So if you scan an item and it doesn't work, the first thing they do is they put in the number, they scan it again. So there are some situations where if things fail, just do it again, right? Then if it still doesn't work, then you can manually enter the number. But the default should not be, oh, let me just give up. If you have something like a barcode in a scanner, it's not that hard to scan it again. If you're in a situation where you are, a nuclear attack submarine, and you're supposed to keep your position secure, you might only surface at certain periods of time to receive a message and then go back down under. In which case, it is not easy for headquarters to retransmit a message to you. I actually have a mathematician colleague who did serve on a nuclear attack submarine at one point. And so it's a very interesting situation where you cannot retransmit easily. And so you need to make sure that you have the correct message. It's the same for some of the messages coming from Voyager. It might be very difficult to transmit some of these messages again. So we want a way to deal with the 2 different types of situations. If it's easy to retransmit, then just retransmit. If you're downloading a massive file, you don't want to download the whole thing and find out, oh, there's a mistake, we have to download the whole gigabyte file again. Although in 21st century, especially on this campus, is it a big deal to download a gigabyte file? No, it's on the order of a few minutes. I will say that when I upload my videos from classes, I can tell when it's spring break or something like that, and I'm uploading the talk I gave, the noticeable difference of not having the students on campus in terms of bandwidth. But even when you're all here and doing all your legal uses of the internet, sorry. So even in that situation, it's still fast enough for most of what we do. So what I want to do is I want to talk about what do you do when you have great concern. All right. So the first is the check digit. So if it's easy to do again, all you need to do is flag that you have an error. And so one of the simplest systems is you're thinking of a scanner at a supermarket. And what you do is the last digit is a check digit. So I want the sum to be either 0, 1, and I want the sum to be a multiple of 10. Or if I'm doing binary, I want the sum to be 0, mod 2. I want the sum to be even. And so here, 9 plus 1 is 10, 17, so I have to add 3. Now it's a multiple of 10. Similarly for the bottom. If you receive something like this, and it doesn't sum to a multiple of 10 or a multiple of 2, you know there's an error. You don't know where the error is, but you know there's an error. What do? You just read it again. So this is the situation where if we can read it without too much difficulty, this is sufficient. It doesn't help us correct the error. All right, not a big deal. All right. So there are more advanced methods you can do. Not surprisingly, if you go to Wikipedia, you can find lots of details on this. There are ways to detect not only if you have a digit error, did you have one digit that was off, but what if you flip two adjacent digits? There are ways to detect issues like that. And it's some really nice elementary mathematics. What's great is you do not need to use a tremendous amount of advanced machinery for problems like this. But even if you do, that can be running off and under the hood and not really see. So here is one way to detect, bless you, where the error is. If I do, tell me twice. I promise to only send 1, 1 or 0, 0. If I receive a 1, 0, what do I know? It's wrong. If I receive a 0, 1. If I receive a 1, 1.
Could be right.
Could be right. So what is the best probability for us for successfully transmitting a bit? What would you love that probability to be? 100%. What is the worst probability? 50%. Why is 0% not the worst probability? Yeah, if you know that you're always wrong and there's only two choices, and this is where it's really important that there are only two choices. Did I mention the George Seinfeld story? Okay, so there are many classic moments in Seinfeld. George is basically a loser. There's no polite way of describing him, right? His life is a horror. And he's having one episode where he's bemoaning to his friends that every decision he's made in his life, every decision is wrong. And so his friends convince him that from this point onward, he should always do the opposite of his instincts. I'll send him the video clips later. It goes from how he starts dating a woman to his interview for a job at the New York Yankees, where George Steinbrenner, the owner of the Yankees, comes by and says, "It's a pleasure to meet you." And his response is, "I wish I could say the same to you." Oh. And he gets the job for being the first person who's actually willing to speak up and stand up to Steinbrenner. So again, it's extremely important that you only have two options when you're doing this. But if you only have two options, being wrong 100% of the time is actually very good. It's being wrong 50% of the time that's worse. And if you've ever taken any subjects in information theory, you often see this P1 minus P coming in to play. You have the most uncertainty when P equals a half. How many of you have seen the Tom Cruise movie, Minority Report? Who wrote the book that this is based on?
Phil K. Dick.
Phil K. Dick, excellent. What else has Phil K. Dick written that has become movies or TV shows?
Do Androids Dream of Electric Sheep?
Do Androids Dream of Electric Sheep, which is? Blade Runner. In High Castle, which became in High Castle. That was pretty easy. I believe Second Variety is often considered as an inspiration for Terminator, but I would have to double check on that one. He's had a couple of stories that have migrated over. So instead of just doing tell me 2 times, do tell me 3 times. And the idea is, hopefully, you have a pretty good chance of success. If you are almost always wrong or almost always right, that's great. If you are right about 60% of the time, that's not so good. Then there's a good chance that you will have multiple errors. But if most of the time you're correct, let's say you're right 99.9% of the time. In a situation like that, it's very unlikely that you would have 2 errors. So if you receive your 101, you are extremely sure that it must be a 111. My son recently did not do so well. I know this is being recorded on a math test. He got every yes/no question wrong. And the reason is the direction said, are the following A or B? And the English was very terrible, and A or B were actually the same thing. So it's like asking you, which of the following are true or not false? So when you get everything wrong like that, when I'm looking at his, oh, okay, I'm not really that worried. You understood all the math. You just didn't understand how they phrased the question. I don't blame you. I'm having trouble understanding the English for this question. So if we are almost always right, tell me 3 times has a lot to recommend it. Why might we not like tell me 3 times? Just before you answer, if you like it, the lecture's over now and you go home. I have no question.
It's not space efficient.
It's not space efficient. What fraction of the message is devoted to information? 1/3. So 2/3 of our message is redundancy. What will you consider the minimum acceptable level for a message for information? I think different people have different choices, but you should give me some number that if it's below this, that's a failure, Professor. What's the minimum acceptable one to be in a conversation? Nobody has any personal preference? What's a good psychological barrier to break? Half, right? Is a half a success or a failure? Do you have to break a half?
51.
51, oh, 50 plus epsilon. As long as more of the message is information than redundancy, we'll consider that at least success. Not a great success maybe, but at least a success. So this is bad. All right, so again, if we get something like this, we can almost surely correct this and almost surely be correct. So these actually might be the Seinfeld links. I will have to double check later. And so we've already mentioned that only 1/3 is information. Any thoughts about what we could do? We did tell me twice, we did tell me 3 times. What could we try next? Tell me 4 times. Okay, that's even worse. And it's not a surprise, right? Now only 1/4 of the message is information. If we continue, we can get worse and worse and worse, and then only 1/4 of the message is information. Why would anybody ever do tell me 4 times?
You're trying to tell the nuclear submarine to launch the nukes.
Yes, and you want to be damn sure about where they target, right? Oh no, it was an accident. I didn't mean to nuke Ambrose. I didn't mean to schedule those 2 groups to meet at the same time. There are just so many errors you could make accidentally that you want to be damn sure when you tell information, right? You actually have something. Oh, I don't know if you guys still have this. You probably at some point in your life had something that had this. CD players, or DVD, Blu-ray players. In terms of how many times they read the information. Why do they have such redundancy?
Because they have the time and people get really annoyed if their movies and songs don't play properly.
Right, so if you scratch the DVD or the Blu-ray, it should hopefully still be caught. If anybody wants to, I'm happy to check that. You can bring your favorite or least favorite, and we'll scratch and see how well it plays. If anybody has like the best of Jar Jar or something like that, that'd be a great candidate to use for something like this. But I think for somebody, they actually read things 16 times. And they have a tremendous amount of redundancy so that they can have the scratches and still going to work. They have so much information that they can store. It doesn't take that much to store a sound. That it's really not a big deal. All right, so we've decided that we want at least 50% to be a success. So this is the real reason I want to give the talk here. It's something like this. It's trying to take a different perspective of something we've already done. So here's a different way of writing tell me 3 times. And now what I'm doing is rather than having it in a line, I'm having it in a different geometry like this. And so the 2 blues are the check digits. And so here, I want this sum to be a multiple of 2, and I want this sum to be a multiple of 2. So I still have only 1/3 of my message being information. But this might give you a suggestion of how to generalize. So this transmits 1 data point. What would we try to do next? And there are several different right answers. So what could we try to do next? Yes?
Fill in the square by putting a pink one in the right corner.
So you could put a pink one in the right corner. And then would that be 2 digits of information we would be transmitting?
I mean, as long as the checks work for both of them, yes. Because you get 2 pinks and.
Well, so if we did that, if this is a 1 and this is a 0, then this would have to be both a 0 and a 1. So it's a good thing to try. And again, this is why I would much rather have a conversation like this than just throwing material at you.
You do 2 pinks and then have the blue the parity check or something?
So you could have 2 pinks together, and how many pinks, I'm sorry, how many blues would you want?
I mean, 1 just to get the better data point, so you're not getting perfect checking it.
Well, we want perfect checking. I don't want to give up on that. So what if we do it like this? I'll put 2 data points, and so what I've done is I basically just added another column. So this check digit checks the first row, and then these 2 check the columns. And if you go through all the possibilities, if there's an error in this one and only this one, then the 2 pinks have to be correct. The 2 blues have to be correct down below, and this has to be the source of the error. So your error is actually the check digit. Unfortunately, a lot of times the message might be transmitted correctly, and it's the check digit that's wrong. Imagine now that the first row is wrong, and the second column is wrong. There's only one thing that's in both the first row and the second column. It's the second pink data digit, and that one would have to be wrong now.
We're both check digits, right?
Good, so we're assuming that there's at most 1 error. And so it's extremely important that there's at most 1 error, because otherwise, exactly as you said, both of those could be wrong. But as long as there's at most 1 error, we can now uniquely determine where the error is. What fraction of the message is data? 40%, that's better. Could you get up to more? Sure, we could just keep adding more and more columns. In the limit, as we keep adding more columns, what do we approach? 50%. Do we ever hit 50%? So we stay below the threshold that we want, which is bad. And also, the size of the message that we're sending is getting larger and larger and larger. What's problematic about sending larger and larger messages? It's related to the issue you have. Where you said, well, what if both are wrong?
Bigger means more chance.
Yeah, if your message starts to get to a great length, you actually have a significant chance now of having at least 2 errors. So we want to keep the message small. So the question is there a more efficient way to do this? So a lot of this was done by Hamming back when he was working, I think it was at Bell Labs. He was the low person on the totem pole. And this was back in the era of punch cards. And he could leave his punch cards on a Friday, and he would come back on a Monday, and they would tell him, okay, it ran to this line, and then it stopped. And then the next week, he would give the fixed code, and it ran another 17 lines, and then it stopped because of an error. And if you mod out the expletives, it was if the machine can detect the error, why can't the machine correct the error? And so it inspired him to develop the subject of error detection, error correcting. And you do not need to use tremendously advanced mathematics for this. And that's one of the reasons why I really like this topic. For those of you who are working now as consultants with businesses, you don't have to use the most advanced stuff. This is a class on efficiency and optimization. Sometimes the best things are the simplest things. So we already said this is only 40%. So here's a much better configuration. So there are two possibilities. There's the triangle spiral and there's the growing square. They both give you 50%. And so if you look at them, I'm not going to go through all the calculations. Let's say the second column and the second row are both wrong. Only one thing is in both. If it's just the second column that is wrong, then it has to be this. And similarly over here, you can go through and you can see that you will detect, as long as there's at most one error, where the mistake is. So which is better, triangle or square? And there is a reason for both. Yes?
Well, it looks like with the triangle, you don't necessarily have to scale as much, like you can do smaller messages.
You can, good.
Result.
So the triangle gives you 50% with only 6 things.
But,
And so you're more likely to be able to avoid having 2 errors. Okay, now you have a but.
well, I was going to say, I mean, if you want to send larger messages,
Right.
The triangle requires, like, you can only add 3, then 4. Like, the amount by which you have to increase the triangle becomes progressively larger, whereas the square can scale a lot more nicely.
But the square is going to get larger and larger as you scale as well. But you're close.
Square is easier to program with because you're just doing rows of data points.
Right, in terms of just visualizing, the square is easier. Is it worth having 2 extra bits easier? Because the computer, you can just tell location. And so with a few lines of code, I would actually say the triangle is better. Now the question is, how would you scale it up? So here's one way to scale up the triangle, is I went to 6 data points, and then 3 of them have to form in some sense like a line, put a check digit on that. And so I put like the super check digit above going through the 3 centers. It works, but it's not pretty. The square is much simpler to do. It's a little bit larger, but it's easier to code. And depending on what you're doing, that's a real trade-off to consider. However, there's a better way of doing the triangle. The better way to do the triangle is like this. And when you see it spiraling up like that and choosing, what I'm doing is basically, here's my original triangle. The next level, the 3 things on the end of the old check digits. I now make those old check digits data digits, and I connect them and put a new check digit there, and then I extend all the existing lines. And so this gives you an idea of how to continue the pattern. It's harder to code, but you only have to do the coding once. And so it might actually be worth doing that. All right. So if you want to actually calculate what the efficiency is, these are the triangle numbers. This is what happens when you have a number theorist teaching a class like operations research. Triangle numbers are extremely famous and important. There's a closed form expression for them, n plus 1 over 2. This is adding numbers 1 plus 2 plus 3 plus 4. We've talked about how to do this many times. You do it by induction. You write the numbers backwards. And so you can see what fraction of your message. So we get n over n plus 2 for our efficiency. So when n equals 1, we get 1/3. When n equals 2, we get 50%. When n equals 3, we get 60%. So already at n equals 3, we have broken 50%. All right. So the question is, we can get as high as we want, but to do that, we're getting larger and larger and larger. Now it's more and more likely to have 2 errors. All right, so is there a better geometry to use? And I'm deliberately stopping here and not hitting. What should we try next? So what is the circle?
Maybe some kind of hexagonal lattice.
So what is a hexagonal lattice? Go 3-dimensional, right? Why are you staying in the plane? If you're flying, say, Delta Airlines or American, I can understand staying in the plane, but over here, why are you staying in 2 dimensions? So this is an extremely important question. This is the whole punchline for the lecture. Do you have blinders on you for certain problems, and do you feel you have to attack them using certain methods? Or can you step out of the box and say, what else can we do? And going to 3 dimensions, really? What should we do? Right, so do we want to do 3 dimensions, maybe 4 dimensions, maybe 5 dimensions? I don't have to physically build this, thank God. The computer just needs to know how to assign the check digits and evaluate things. So, this should not surprise you. I will use Rubik's Cubes to illustrate these points. Okay? So here are two very nice Rubik's Cubes, a 2x2 and a 3x3. The 2x2 has 8 bits. The 3x3 has 26 or 27, depending on whether or not you include the center. And so you can see what's going on in terms of your efficiency. All right, so we're running out of time, so we're not going to go too much. But you can keep looking at what fraction we get. Not surprisingly, as the cubes get bigger and bigger and bigger, you're doing better and better and better. And what you want to do is you want to talk about how would you find an error. So for instance, over here, I have 3 planes going in this direction. I then have 3 planes going in this direction, then 3 planes going in the other direction. And so the planes will intersect in how many places? Well, 2 planes will intersect in a line, 3 planes will intersect in a point. And that's why I am including the center. And if you go through the analysis, you can see that for each of the planes, I assign a check digit. And so the number of check digits is going to be equivalent to the number of planes I have. And this is where the efficiency is going. So what you can then do is you can see how many points do I need to use to get different efficiencies. So for 4x4x4 cube, I've got 64 data points, 12 check digits, for an efficiency of 84.21%. For the T11 triangle, I have 66 data points, and the information is 83.54%. So it's a little bit better, it's a little bit worse, in terms of efficiency and data points. So it's got 79 points that I'm transmitting and 66 of information. Here I'm transmitting 76 points and 64 information. So the new higher dimension is actually beating the better shape of the triangle. What should I be using instead of cubes?
Hypercubes?
I'm sorry, well, hypercubes is yes, if I want to go to high dimensions. But maybe there's something I should be looking at here instead of a cube. A tetrahedron. The triangle was actually beating the cube for a certain number of points. So maybe we should look at tetrahedron. I really don't want to do that. Geometry, so I will skip that. But I will talk briefly. And what is this one called? Is this the megamix or duodecahedron?
It's a megamix.
So it's the megamix. Right. Now there's various forms of the megamix. Okay? What you can do is each one of these is going to be data, and then you have to decide how do you want to assign your check digits and where do you want to assign them. The earlier ones don't actually have anything in the centers here, and it's essentially just like a souped up 2x2 cube. My students last summer were finally able to teach me how to do this. You can put stuff in the center, in the middle of the sides as well. And then you can see what kind of efficiencies will you get here. And then the question is, can you keep extending this? Or do things break down? How can you keep adding all these different check digits? So I will just end very briefly by mentioning Hamming codes. I'm curious to see how many people have seen Hamming codes. Okay. So I've shown you how you can use geometry to do a little bit better. Here is the best solution. And once you have it, it doesn't matter how you found it. It's the method of divine inspiration. You can write it down and go through and show that it works. So this uses 7 bits of data to be transmitted. And of those 7 bits, 4 of the things you care about. So the only thing I will give, I'll tip my hat to New York City, is for the wonderful grid system of Manhattan. Almost everything else I hate. But, growing up in Boston, the geography of Boston. Anybody know why Back Bay is called Back Bay?
Because it used to be part of the Charles River.
I don't know if I'd say Charles River. It used to actually be a bay behind the city, and it was filled in. You have streets that cross each other in Boston and change as to which one is north of the other. The geography in Boston, so Manhattan is a beautiful grid. All right, so what I'm going to do here is I'm going to imagine a subway system in New York. I will have 4 data points. I'll call them D1, D2, D3, and D4. And then 3 points on here, P1, P2, P3. And I'm going to connect P1, P2, P3 as shown here. And so what you can do is you can go through all the different cases. And we will assume that there's at most 1 error. And so what I do is I sum for P1, it's connected to D1, D2, and D4. So I choose P1 so that the sum of those 4 things is even. And imagine that everything is correct. That's great. If all the check digits are wrong, well, what would go on if every check digit is wrong? Is there anything that they all go to? Yes, they all go to D4. So if every check digit is wrong, the mistake has to be with D4. And so you can go through the other cases, and you can see that this will allow you to detect and correct any error, and 4/7 of your message is information. There are more advanced methods of Hamming codes. Any idea what comes next? This is using 7 bits. What do you think might come next? This is tough to tell.
8.
Not 8, not 9, not 11, but 11's getting closer.
13,
13's getting closer, but still not quite there.
16.
16's way too high.
14.
14's way too low. I believe 15 is next. So what do like 7 and 15 have in common?
They're both 1 minus 2 to the n.
Yeah, they're both 1 less than a perfect power of 2. So when you're doing a lot of these analyses, certain configurations, certain numbers are going to work out better than others. We actually saw this when we did the Strassen algorithm for fast matrix multiplication. It's nice if your matrix is a perfect power of 2. So when you're doing this stuff, one of the things to be aware of is what's the best configuration to look at. So here's a comparison. I'm transmitting around 4,000 bits of data. The square gets you 96.9%, the cube 98.8%, Hamming gives you 99.7%. They're all damn good, at this point. But Hamming is a couple percentage points better. And these small little gains can become tremendously important. So this goes back to the Horner's algorithm and all the stuff we've been seeing throughout the semester, that there are things you've been doing all the time. And if you spend a little bit of time in the beginning thinking, you can often find a better way, which then pays tremendous dividends going forward. My brother mentioned this to me. This is great. Let's say you want to transmit the following string, but there's a localized burst of noise that destroys things right there, but everything else is fine. So imagine there's a solar flare. The problem is, when we receive the message now, we need to assume that we don't have 2 bits of error in small segments, and now we might have that. There is a trivial, simple way to fix this. You need to know the entire message beforehand. But that's not unreasonable. If you know what you want to transmit, you have the whole message before. And so what you do is you break the message up into fourths. Now, in reality, you might break it up into 100 parts or 1,000 parts. And what you do is you transmit the 1st, 5th, 9th, 13th, and so on. And so what you do is data bits that were close to each other in the original message are now spread out when you transmit. And so if there's a localized burst of information, it's not affecting digits that are all near each other. So that when you reassemble it at the other end, it's much better. The problem with this is you can't really do anything until you receive the entire message. But we talked, I think, about steganography earlier in the semester, hiding messages and messages. So since we've already done this, did I actually show you the pictures? Okay, so this is a tree. There's a cat hiding in the tree. And so the way we described it is, let's say you have an L by W grid. The pixels are either going to be red, green, or blue. They can take values from 0 to 2 to the n minus 1. So we do 256. That gives us a little bit over almost 17 million colors, which is more than enough. And so what we can do is, let's just take one of the colors red. We can write its number in binary. And if we just change the last 2 digits, it's really not going to change the color that much. And it gives us either 1 or 2 bits to play with. And again, you can also do this for the green and the blues. And so by doing that, we can actually hide a cat. And so the cat is technically in the tree. Or maybe that's why the cat's belly is so big, maybe the tree is in the cat's belly. Is that a really good picture of a cat? When you look at this picture, what might you notice?
Kind of green.
Yeah, it's kind of grainy. Why do you think it might be a little grainy?
You don't have that very many colors.
Yeah, we don't have as many colors. And that might also impact a little bit of the tree over here in terms of how sharp that image is. So, if you're willing to do a more complicated program, you can even alternate maybe between which color, red, green, blue, are you adjusting the pixel on. If you only want to send a text message, if you want to take something that you've written in Microsoft Word, you just have white and black bits. That's much easier to transmit. And you can actually hide text and messages. And so, of course, the question is, if somebody transmits something to you, can you tell that they have hidden something in it? Right. So, the point for today was to talk a little bit about how do you attack a new problem? How do you deal with issues of efficiency? Is it worth spending some time at the beginning to try to come up with a better way, or is it not going to matter? For a lot of things now, we don't really have to be so concerned because processing power is so good. Disk storage, it's so cheap. You don't have a lot of these issues. But there will be situations when they do matter. And then for the last minute, I mentioned before class that the Cincinnati Bengals, in some sense, for the postseason, it didn't really matter what they did yesterday because they had already been eliminated from the playoffs. And it's extremely unusual to be eliminated in the NFL after only 10 weeks. It's happened a few other times before, not often. As a nice problem to think about, write a linear programming problem, or think of how you would do a linear programming problem to determine when somebody has been eliminated from the postseason. Now, in Major League Baseball, they actually did this incorrectly in 2004. They said the Red Sox clinched the wild card one day after they actually did. And the reason was, if the Sox lost every game and the A's won every game, the A's could surpass the Sox. And the Angels, if they won every game, could surpass the Sox. But the Angels and the A's, one of them had to win the American League West, and they had a 3-game series against each other. What will happen in the 3-game series? Someone will have to lose at least
More than 2 games.
at least 2 games. And so it's not possible for both teams to win out unless if one of them does win out, they would actually win the American League West. And so it's an interesting question as to how do you calculate the true elimination number for a team. You have to take into account all possible games. You can do it for each team individually, but there is a great website that actually does it for all teams simultaneously. All right. Yeah. All right, so this is a good place to stop. Enjoy Thanksgiving.